Evening, everybody. It's 5 p.m. Thursday. Time for some Calc 2. So last time was just a very general introduction class. We just talked about the class. Today we'll start to feel a little bit more what class is like. Almost everybody went through the lesson for today, which is perfect. Guys, I can't emphasize that enough. Going through the lesson, taking notes, you will get more out of the class that way, okay? Because when we come in here, because of the amount of time we have to get through everything we want to get through, I have to assume you've at least looked at the lesson, because once we come in here, I'll start talking about the topics from that lesson. And, you know, for you to be prepared, you need to make sure that you've seen the lesson. Again, like we talked about before, you don't have to finish it. If you didn't get 100%, that's fine. You can do that later. But definitely want you to have gone through it before class. We'll have some time at the end. If you guys have any questions about, now that you're starting to see what the lessons are like and what more is like, at the end of class, if anybody has questions, we can go over that. But what I want to do today is just kind of start to get the feel for a normal class and go right into what we're going to talk about today, which is integration by substitution. And what I'll do in a normal class, as you'll see, is I might go over something from the lesson. I might go over something from the book. I might pull something else off the web to get us started. And then we'll look at a couple of examples. Since this first module is all about techniques of integration, we're going to spend a little bit more time just doing some examples of these techniques and probably a little bit less on the conceptual. Now, when we get into future modules that are a little bit more conceptual, we'll spend more time on the concept and less time on the examples, so on and so forth. Okay. And as we're working on problems, guys, I have chat up. So you can always post something in chat. And every once in a while, I might miss it in chat because I might be focused on the whiteboard. If that's the case, just turn on your microphone and feel free to ask a question if questions arise. All right, let's dive in. Let's go work some problems, see what kind of questions come up. This week, I really want it to feel a lot like review. Most of you guys have done U-Substitution before in Calc 1, so you've seen it. So it probably felt a little bit like a review, which is great. That's what we want, because starting next week, we'll start to get into more complex techniques of integration. And we need to have the basic rules and U-Substitution down before we can move on, because there's going to be integrals where we might use more than one technique. So our goal today is really just to focus on U-Substitution specifically. And this first module, keep in mind what our goal is. Our goal is to try to figure out how many of these integrals we can solve by hand. And then we'll also talk about how we deal with the ones that we can't. So let's take a look. I got a few examples I want to go through for U-Substitution, and I'll talk about U-Substitution as I go through it. So first one, I have the antiderivative of e to the negative x. I'll point out a couple of things just because we're doing integrals together for the first time. For instance, notice there's no limits. That makes this an indefinite integral. And so the answer will be a family of functions. If you remember from Calc 1, you need the plus c when you have an indefinite integral, unless you're given some kind of initial condition. The next thing we would notice is we have more than just a basic antiderivative, right? One of our favorite functions in calculus is e to the x. Well, what's the antiderivative of e to the x? And when I ask questions, you can type in chat, perfect, or you can always turn on your mic and answer. So this is our favorite because this is the one function who is its own derivative and its own antiderivative. Now, because we have an indefinite integral, we put a plus c on there. Now, what we want to look at, though, is when we have more than just e to the x, like in this case, e to the negative x. If you remember back from your derivative rules, if we were taking the derivative of e to the negative x, it'd be a chain rule. So that means to do the antiderivative, we actually need to undo the chain rule. So U-substitution is all about undoing the chain rule. I'm going to show you how I like to do it. I'm going to show you a couple different things from the notation as well as we go through this. And feel free to, if any questions arise, let me know. Like I said, I think the U-substitution, judging by the scores on the lessons, you guys are pretty comfortable with this already. But I just want to show a few of the nuances and see what kind of questions might come out. So whenever you're doing U-substitution, you'll have an inside and an outside function. Now, it may not always look like that. Maybe hard to tell what's inside and what's outside. Sometimes it's very easy. But think about what we're trying to do. We're trying to undo the chain rule. Well, the chain rule is when we have a composition of functions. So there's an inside and an outside. So I'm looking at this one. I know the negative x is what's making this not our basic antiderivative rule. So I'm going to let u equal e to the negative x. Now, excuse me, sorry. I'm going to let u equal negative x because it's just that exponent that's the issue. Now, I want to talk a little bit about what happens next. Our goal is to get all the x's out and get it all in terms of u. Once you choose u, then you calculate basically du dx, which is the derivative of u with respect to x, which is just -1. Now, a lot of times when we don't see it written this way, this dx gets cross-multiplied over here. And I normally won't write it this way either. You'll normally see me write it this way, -1 dx or negative dx. All right, I just wanted you to see where the dx notation comes from. Now, we're ready to make our substitution, but there's one thing that isn't in there. I have a dx in there, but I would need a negative dx. So I'm going to show you how I do it, but I'll also show you another way. So what I do is I say, oh, I need a negative dx in there. Well, I just changed my original to have a negative dx right there. So to make sure I compensate for that, I put a negative out front. So whatever I do inside to make my substitution work, I undo on the outside. We can always do that by a constant. Because now I can make my substitutions. This negative x, well, that's u. And negative dx is du. And now we have a basic antiderivative. As you guys told me before, the derivative of e to the x is e to the x, so the antiderivative of e to the u is e to the u. It's an indefinite interval, so we need a plus c. Okay. Question for you guys. Are we done?
No, because you need to resubstitute back the u.
Perfect, John. Yeah, guys. And I know this seems trivial, but I want to make, I want to stress this point because as we get into other problems, we might be dealing with different variables than x and u. We might be looking at multiple techniques of integration in the same problem. So we want to pay attention to when we're done. We're not done. Our problem started in terms of x. We want to end in terms of x. So as John said, we want to sub back. U is negative x. So negative e to the negative x plus c. All right. Now, I want to show you one small variation of this that I know some people like to do, which is totally fine. All right, so you've got your e to the negative x dx. It's just, I use what I do in blue there. Let's just say, so we let u equal negative x, and then our du is negative dx. And then for the substitution part, what some people like to do is actually solve for dx. So, we divide both sides by a -1, and we get dx equals negative du. And sometimes this may feel like a little bit easier substitution route. So now when we sub, here goes our u in there. So e to the u. And what we'll do is we'll put a negative du in for this guy. Now we'll pull that negative out front. So negative e to the u du. And you can see we get the exact same thing. So I want you to do whatever you are most comfortable with. When I'm doing problems, examples, you'll see me do it like I do in the blue. I like to change what's in the integrand and compensate outside. But I know there's a lot of people who like to solve for the dx and do a direct substitution. Neither way is better or harder or worse than the other. So kind of user preference on that. I just wanted you to know that both ways are fine. Okay. Questions about that? I'm going to put the link to this whiteboard in chat so that you have it. So that's the link to these whiteboards that I'm using. I'll be able to push these out to you when you guys are working on problems. Okay. Let's go with a little bit more interesting example. That one was a little bit on the basic side. So we get a function like this. I think when there's something like this, it's pretty obvious what the inside is because it's under the radical. If that weren't so complicated, we could deal with this a lot easier. So I'm going to let my u equal the 2x squared plus 1. Now, when you're looking for your u, another thing that we need to make sure is that we can get the du in there. For example, if this x was not here, this would not be a u substitution problem, because look what happens when I get my du. 4x dx, I'm just taking the derivative of u. Well, I need another x in there in order for this substitution to work. If this had been an x cubed, we probably wouldn't want to use u substitution. So we want to make sure that what we choose for u allows us to also to get du in there. Now, there's too many variations, obviously, for me to go through all of them. You saw some examples in the lessons. You're going to see some more examples in the homework. You're going to work on some more examples today. And you'll get used to it, choosing your u in a lot of different situations. Okay, now, like I said, I have my way of doing it. I know I need 4x dx in order to make this substitution work. So I need a 4 here. Well, I put in a 4, then I got to multiply by a 1/4 because I do not want to change what I have. So that's how that works the way that I like it. The other way of doing it, like I said, solve for dx, right? So dx would equal du over 4x, and then you do a straightforward substitution. All right. So there is my du. This is what I let be u. So I have 1/4. The 4x dx is du. And I end up with square root of u. Now, as a reminder, when we have a radical, we change this to be a fractional exponent. So 1/4 times, 4/4 the integral of u to the 1/2 du. And now we can do our antiderivative. And here's the way I like to think of the antiderivative of our power rule. Increase the power by 1, divide by the new exponent. So 1/3/2. There's my antiderivative. Now, one thing we never want to do is leave a fraction in a fraction. So we're going to clean this thing up a little bit. So 1/4, 1/3/2 is 2/3. U to the 3/2 plus C. And like you guys told me before, we're going to have to substitute back. We can also clean up this fraction a little bit. Both those are divisible by 2. So 1/2 times 1/3 is 1/6. And we put our u back in there. So 2x squared plus 1 to the 3/2 plus c. You do not need to rewrite that half fractional exponent as a radical. You could leave it as 3/2. In fact, I think this is easier. If you wanted to, you could say 1/6 square root of 2x squared plus 1 cubed plus c. But I think this is perfectly fine for this kind of problem. All right. How we doing? Any questions on that? Excellent. Okay, we're going to do one more, and it's only because I want to do one that's a definite integral, because there's one thing that I want to show you that I like. Again, this is going to be a user preference thing, but I have a reason for liking it, and I will explain that here as we go through the problem. So right off the bat, you see limits, definite integral, meaning our final answer should be a number, as opposed to a family of functions like we got in the last two. And when I say a family of functions, that's what the plus c is doing. Because without the plus c, it's just a single unique function. But the plus c, every time I change c, I technically get a different function, but it has all the same characteristics of this function. Hence why we call it a family of functions. Definite integral, we should get a number. One of the nice things about definite integrals, we can do definite integrals with actually our graphing calculator. If you're not sure how to do that, send me an email and I can send you a video on how to do that. But it's nice for checking the answers. So let's go ahead and do this one by hand. We need the inside and outside. We need to find our u. And you know, a lot of times du will never go in the denominator. So looking at the denominator for u is a good place to start when we have a rational expression in our integral. So our u is going to be x squared plus 9. We can, once we have our u, we can calculate our du, 2x dx. And we can get to work on our substitution. Like before, I have an x dx, but I need 2x dx, so I'm going to put a 1/2 out here. And now I'm going to start to do my substitutions. So I got 1/2. There's my du right there. And this is up to you. You can write du on top, and then this is our u. Or some people like writing it this way, 1 over u du. Okay, oops, that should be a u, not a w. Those are the same, guys. Either way is totally fine, whatever you're more comfortable with. Now, here's where I would like to recommend this for you, but you do not have to do it. Now, 1 and 2, those are x values. That's x equals 1 and x equals 2. My integral is in terms of u now. So if I were to put 1 and 2 here, like so, That's technically not correct because those are U values and those are X values, but it should be U values. So what I like to do and what I like to recommend on definite intervals is changing the limits. Is it necessary? Absolutely not. And I'll talk about the alternative here in a second. But how you change the limits, well, here's your exchange between U and X. So when X is 1, so 1 squared plus 9. So for the limit of 1, where X is 1, U would be 10. And U equals 2 squared plus 9, or 13. So those are limits in terms of U. Reason I like doing it this way is because now I'm just working from here on down. So this could be put into the graphing calculator, for instance, or I don't have to worry about substituting back because I do see that mistake happen. Also, right now, U-substitution is going to be our focus. Next week, when we get more techniques of integration, we might have a problem that needs several different techniques to solve. And this actually will simplify things because then we don't have to sub that. Again, not required because you can always just do it like we did the other problems and then sub back and then put in your limits 1 to 2. But this is just my recommendation. So we need another basic antiderivative. What's the antiderivative of 1 over U? Very nice. Natural log. Now, technically we do need the absolute value for the general antiderivative. The reason is because 1 over U is defined for all reals except 0. Natural log of U is only defined for positive numbers. So to make these actually match up, we use the absolute value. We don't need the absolute value in this one because we're going to be plugging in numbers that are already positive, but it's not going to make it wrong either. All right, so if you did put in the absolute value, that's not a problem. And then we have to put in our limits. So we put a line behind. This is just a little review of this notation. Notice the integral symbol turned into a line behind. This tells the reader that the antiderivative has been taken, but the limits haven't been plugged in yet. So we have 1/2 upper limit, so ln of 13 minus ln of 10. And guys, this is fine for a final answer. It's nice and exact. It's not a decimal approximation. If you want to get fancy, we can use some properties of logs. Subtraction of 2 logs, this should look familiar. Ln of A minus ln of B equals ln of A over B. We can make this ln of 13 over 10 or ln of 1.3. These are the same answer, guys. More would accept this answer or this answer. So I'm not telling you have to do this, but for those of you guys who like playing around with properties of logs or like looking at answers that are equivalent, having the 1/2 out front, if you remember, that can actually go up in the exponent of a log. So 13 over 10 raised to the 1/2 power, or ln of the square root of 13 over 10. Again, we were fine here. You guys are done here. Just a little, I had the opportunity to review some properties of logs, which will come in useful in some future problems. So I just wanted to take that opportunity. Notice our final answer is a number. This is nice and exact. One of the things I will stress in here is when possible, we love exact answers. All right. As soon as we turn this into a decimal, we have to round it off somewhere. We've introduced round off there. So whenever we can be exact, we try to be exact. All right. Okay. Questions about this one? All right. Okay. Then we are about to break into groups. But there's something I want to show you because I don't know if everybody is aware of this site. Now, we've talked in here a little bit about Wolfram Alpha. We will use that on occasion. Desmos, we might use that every once in a while. But here's one that I don't know if everybody's seen, and it's called Symbolab. Okay, and it's just symbolab.com. Now, here's why I'm showing you this one. Notice all the math symbols. So let's go back to problem B. Let's go back to this one. All right, so we did the integral of x times the square root of 2x squared plus 1. There's our integral symbol, x, and then square root 2x squared plus 1 dx. And here is some of the steps of our integral, and check out what our final answer comes out to be. 1/6 times the quantity 2x squared plus 1 to the 3/2 plus c. Looks familiar, right? Right there. Now, I want to talk to you about why I'm showing this. Please realize that, when it comes to the exams, the proctored exams, you will have to solve some of these integrals by hand. Not really, really complex ones, but ones kind of like the ones we looked at just now. But when you're doing homework, when you're working in groups, when you're doing problems for the take-home, Symbolab is a great tool for checking your answers. And what's really nice about it is the problem entry, because of this toolbar, and you can expand the toolbar, will allow you to put in the problem the way that you're seeing it. Okay. So when I wanted to show you this because we're about to break into groups, and you're going to work on some integrals, and you might want to say, well, we got this answer, but we want to check and see if it's correct. Symbolab is a great way to do that, to make sure that you're getting the correct answer. And then if you're not, you can retry the problem. You can call me into your room, and I can take a look, and we can see where we might be having issues. Okay, so Symbolab is a great tool. I want to make sure that everybody is aware of it. We will get some opportunities to use Wolfram Alpha, and probably try and use Desmos once or twice. We're not doing any graphing right now. Maybe next week or the week after we will. But Symbolab is one I wanted to show you because we're about to go into groups, and it's one you could use to check your answers. Okay, but I don't want you to become overly reliant. Think of Symbolab as a way to check your answers, but not a way to do your homework. You do your homework, use Symbolab to help you out. Okay. All right, so here's what we're going to do in groups, and I'm going to put this into chat. We're going to do some problems from the textbook. All right, how many? Okay, we're going to do 4 groups again. And I'm going to give each group one problem from each activity, and I'll show you what I mean here in just a second. Every once in a while, we use the book. Sometimes we use worksheets. So here's the book over on the right-hand side of the screen. And if you scroll down, you'll see you get to activity 5.3.2. So group 1 is going to do part A from 5.3.2. You're going to do part B from 5.3.3, which if you scroll down is a little further, 5.3.3. You don't have to do all of these parts. You just have to do the antiderivative. All right, so each group is going to do 3 antiderivatives, one from each activity. I'll also put the link I'll send the link out once you guys are in groups as well. But I just wanted to show you that that's where the problems are coming from, so that, you know, so that way you have the problems in front of you to work. Just like last time, you know, if you guys can use one of the group whiteboards, that'll help if I have to come, if I come in and there's any questions, because I can see what you're working on. But if not, that's okay. You can always show me a picture or something. But like I said, you can always work on your own paper as well, because after this, you're going to upload your solutions. And guys, this is what we're doing for the rest of today. I'll pull us together towards the end again to see if there's any questions and recap. You know, so once you finish all 3 problems and you check them in the Symbo lab, and you guys are happy, call me in and let's chat. Okay. So let's get you guys. Well, before I break you up, are there any questions? Okay. As a reminder, I'm also starting to record the lessons today. So if for some reason you decide to leave class early or anything. All right, guys, welcome back. Great job today. So just remember, if you want to get the credit for the points today, you want to upload your own. You know, everybody's got to do their own set of solutions. You can't do it as a group to the forum, and it just needs to be done by the beginning of the next class period. So since all you guys are already done, you might as well do it after class and get it over with. But as a general rule of thumb, you know, that way, if there's a problem you didn't finish that you want to work on later, that's totally fine. You'll always have until 5 p.m., which is the start of the next class, to get those uploaded for credit. And that, again, is optional. Yeah, jump on.
So are you going to make a new forum for each day that we have class, or do you just want us to put it in the same solutions thing that we have already?
We're just going to put it in the same solutions one we have already, and just put the section number and, you know, the problem number or the activity number in the title.
Okay. So all of the different problems that we did.
Now, since if you did, you can put all the problems in a single post.
Okay.
So you could say, so like today we did, so you could do section 5.3 ABC would be fine.
Okay. So, or like, could we say group 4 if I'm in group 4 then, if that makes it simpler? Or...
You can. You don't need to put the group number, just so people know what problems you're looking at. That's all.
Okay.
But yeah, good question. We're just going to keep the same forum, because otherwise it get too congested with other forums. So we'll always post to the same forum, and in your header, just put what section and which problem or problems you're posting. And if it's more than one problem, just put them all in the same post. And again, that's not, you can do that anytime between now and 5 p.m. Next Tuesday. Okay, so coming around to the groups, I know some, you know, we're at different places of levels of rust with our anti-derivatives. But this is a good week and weekend for those of you guys who maybe need a little bit more practice to do so before we really start cranking it up the next couple weeks with some more techniques of integration. So make sure, you know, you're getting the practice that you need. There is that review assignment and more. It's not due for a couple weeks, but for those of you guys who maybe need a little bit more practice, this would be a good weekend to do it. And it's a good weekend to get it out of the way. You now have the homework for this section as well. I'll be putting up the video from tonight and the whiteboards. They'll go in more at the bottom. You'll see that there's when you go in there tonight, you'll see there's a block there, and that'll be where everything's kept. Excuse me. So I don't have a whole lot to recap today. You know, you guys did great with the U-Substitution. Remember, if it's an indefinite interval, it needs a plus C. If it's a definite interval, it should be a number. Past that, it's going to be just getting some practice with the U-substitution, which is what you're going to get from the homework. That said, we have some time left. Let's start off. Any questions? We'll start off with any general questions because this is our first week. Any questions about uploading solutions, the lessons, anything of that nature? Like I said, we're still in the first week, so if it doesn't feel familiar yet, it will. It will really quickly. I think by next week, you'll really get into the hang of, oh, got to do an online lesson before class, meet in class, we'll work some problems, post those to the message board, and then work on the homework after class. So you're kind of getting that routine. Okay, then guys, we got 15 minutes left. Any questions about 5.3 or U-sub that you guys would like to look at? Problems? Yeah, Dylan.
Yeah, I have a question about the title for the post.
Sure.
I put for the subject, I just started a new thread and put the date, and then I made like the problems. Is that what you wanted? The section and the problem?
Yeah, that's perfect.
Okay, cool.
Perfect.
Okay.
Absolutely perfect. Thanks, Dylan. Yeah, and when you're putting the header, just think of what you would want to see from somebody else's post, right? If you wanted to say, I want to find the solution to activity 5.3.2b, how am I going to find it? So just put in your header what you'd want to see from somebody else's. Is probably the easiest way to put it. There's no real, you're not going to lose points if you didn't include the problem number or anything. Just think of it from hey, we're trying to share our solutions standpoint. So the more information, not more information, but if you can tell people what problem number, that's going to probably be what's most helpful.
I guess I gotta probably just looked at everybody else's title and gone with that.
Yeah, you can see what other people are doing too. That's totally fine.
Yeah. Cool,
I don't want you guys, but don't stress out about it. Just enough so people know what solutions they're looking at.
Okay.
Other questions? And guys, if you don't have questions, we are done for today. That covered everything I wanted to do. You guys knocked out those problems really quick. So if you want to take off a few minutes, a little bit early, feel free. I'm just kind of hanging around for anybody who has stuff they want to go over from the lesson, from stuff we did today, etc.
Yeah, if you could just do one or two worked examples.
Okay. Do you have any in particular?
I mean, you could do have it written down. Hang
Oh,
on.
sorry. Which one? I couldn't quite understand.
I'm just I'm trying to find the one I want you to do.
Okay.
The
Yeah,
third
grab one from-
So 5.3.4b.
5.3.4b, this one right here.
Yeah. Mhm.
All right, let's take a look. All right, so we have a definite interval, so we're going to get a final answer of a number. So 0 to 1, e to the negative x, 2e to the negative x plus 3 to the 9th dx. Now, this 9th power is kind of what's tipping me off to what I might want to be u, because this is really, to try and multiply this out would be a huge mess. Oops. So I really want to try to simplify that. So I'm going to look at letting u be this inside piece right here. 2e to the negative x plus 3. Okay?
All right.
Because that'll simplify this down to u to the 9th. Now, we need to make sure we can get the du in. which is basically the derivative of this guy. Now, the derivative of an exponential is itself times the derivative of the exponent. That comes from our chain rule. So I know the du is 2e to the negative x times the derivative of negative x, which is -1. Derivative of 3 by itself is just 0. So I can put the dx up. Let's clean that up a little. And as I'm going through this, if you guys have questions, let me know. So now let's see about making our substitution. And I want to change colors for this because I just want to make this real obvious. So if I'm looking at this, I already know this part here is, so that part I'm done with. This e to the negative x is going to come in handy because it's going to match up with that e to the negative x here. So that e to the negative x dx is going to be part of my substitution. The only thing missing is that -2. So I'm going to put the -2 in there because that there, hopefully this isn't getting too messy, that there is my du. All right.
So are you supposed to just like make everything other than u look like du?
Other than
So like you have u, and then like whatever's left over in the integral, you have to like make it the same as du.
yes, what I need to here's the way that I look at it. We get to choose u, so we do that, and then we calculate du. Then what I need is to make this be in my integrand so I can substitute in the du.
Okay, I see.
Now, because I put that -2 in there, I've got to compensate for it outside with a -1/2, because now I haven't changed the original integral. So we've got the -1/2 out front. The -2e to the negative x dx is du. So we end up with u to the 9th du. This is nice because now we're down to a very basic antiderivative. Now, like I said, I like changing the limits, although they're not going to be very pretty on this one no matter what we do. Because if x equals 0, we have 2e to the -0 plus 3. E to the -0 is 1 times 2 is 2 plus 3 is 5. So that's our new lower limit. And then this one, not much we can do. When x is 1, that's our upper limit. It's not pretty, but it does save us having to sub back. And now I only have to focus on the antiderivative in red. I'm done with what's up in the purple. So -1/2. Antiderivative of u to the 9th is u to the 10th over 10. And that's going to go from 5 to 2e to the -1 plus 3. We can multiply these together to make it a little cleaner, make that a -1/20. And then we'll plug in our limits into the 10th power. So 2e to the -1 plus 3 to the 10th minus 5 to the 10th. And because this is going to be a mess no matter what we do, I'm just going to leave it like this. This is a nice exact answer. It's not pretty, but it's exact. If we wanted to get the decimal approximation, we could put that into a calculator or a Wolfram, but this is perfectly fine for a final answer.
Okay.
Questions
All
about
right. I think that makes sense to me. Yeah.
Okay. And like we were talking earlier, it might take some time to just get back into the flow of doing the antiderivative process. And that's just going to come with practice. Going through the review assignment and the 5.3 assignment, I think is going to help.
Yeah, I think I'll be good.
Yeah. Okay, other questions about this problem or anything else you guys want to ask about? And guys, it's totally fine if you don't have questions right now. You can always email me questions later. I do check email over the weekend. Also, you have access to online tutoring over the weekend as well. But sorry, I might have cut you off. Any questions? Okay. But yeah, guys, take advantage of the forum and the tutoring over the weekend if you have questions while you're working on problems. Okay, that's all available to you. You know, everybody in the class will be looking at the forum. I'll be checking email, and you saw remember the tutoring resources folder right here. SCC offers some online tutoring on Saturdays, and you also have access to BrainFuse online tutoring over the weekend. So just don't feel like you can't get help on over the weekends, okay? All right. All right. If you guys don't have any other questions, we'll go ahead and end a few minutes early. Once the video is done processing, I'll get that uploaded to more in case you want to review anything. And we will move on to the next section on Tuesday. Again, if you have questions over the weekend, forum, tutoring, email, you can ask other people from class. So make sure you get help when you need it. Don't feel like you have to wait until Monday. All right. All right, guys. Have a great weekend, and I will see you guys on Tuesday.